Good morning, everyone. For those people who are here for the network performance session, can I get you to take your seat, please? We're about to start. We've got a great lineup this morning of 4 presenters that are going to be talking about various topics to do with the network performance. We're going to start off with Randy, who will be talking about debugging routing and forwarding using RIPE Atlas. So can you put your hands together and welcome Randy to the stage, please?
1, 2, yeah. Okay. So many years ago, Daniel Kahrenberg said he was going to do this RIPE Atlas thing, and I'm an experimenter. And I said, well, what's the experiment? And he said, nothing in particular, it's infrastructure. And I didn't understand it. And I said, and I ignored it. And now I use it every week. And instead of standing up here and telling you RIPE Atlas is this wonderful thing with 10 million nodes, etc., I'm going to give you a couple examples of actually using it to debug two real problems. And the example problems were, I'm going to do these 2 in order. The first one is for a POP. I had a serial controller. And of course, when you have a console controller in your POP, you don't want it relying on the network connectivity of the POP to be able to debug the network connectivity of the POP. So that serial controller is connected to a whole nother network. And it was the colo provider's network, which was generous of them to let me connect to it. But they made some changes and the server became unreachable. And they wanted working on debugging it. No resolution for a week. The second example was a friend had, from an ISP, a big fiber ISP, had connectivity to his home office. IPv4 worked, IPv6 didn't. Their NOC said everything was fine, as NOCs always do. So, what do I use? RIPE Atlas, which you know is a whole bunch of small devices all over the world, or you can use your own VMs, etc. Yeah, thank you, Leah. And so anyway, there's a whole lot of them, and you can create measurements. And when you do, you can choose how to select which probes to use. Okay, and The Colo folk in the first example were very cooperative, but they couldn't find the cause. And they kept debugging for days. It took me 4 days to say, let's use RIPE Atlas. So I used a global, so from anywhere, random trace route. Okay, and it said nobody could reach the target. And then here's the result. And you can see coming from a bunch of probes and dying right there. Okay? And once we'd spotted this, they fixed it in an hour. Once I could say, that router is not working. Okay? And so this is the trick. Okay? The darn thing comes from many probes, and you can do them from all over the world, whatever you want, select them. It gives you the trace routes towards the target, and here's the failures. Okay? So, the other one was Tom's IPv6. Their NOC could not see any problem. This had been going on for months. I wrote to their NOC. They didn't even respond. So I posted to the NANOG list, and someone from the same ISP could not reach him over IPv6. So that says, oh, that ISP has internal routing problems. So I said, let's not do a global probe selection. Let's just do it within the ISP. So here we have the result. 2 probes could reach the target, 13 did not. So the ISP has an internal division of their topology. And here's the trace route. Here's the ones that worked, right? These 2 probes could get to Tom. The rest of the ISP's network couldn't. So they have a partition in their network routing for V6. There's this newer way to visualize it. This is taken from actually Massimo Scandella's paper. I forget what they're calling it. I'm not very fond of it because this doesn't visually say to me as clearly as the previous one did. This one, I really felt I could see the division in the 2 networks. This one, less so. But it's whatever flavor you like. So a senior engineer at the ISP saw it, fixed it in a few hours. And indeed, it was an internal routing problem, just as you expect. So, and the senior engineer had a little talk with the NOC who had spent months saying there is no problem. For RIPE Atlas probes, it's not only that I can go to the web page and configure a measurement and debug, there's also an API. So there's the web interface, there's the API, there's a CLI interface, there's all sorts of things, streaming output, BigQuery output, etc. But the API lets you get a typical API key, you compose a measurement in JSON or whatever, you stuff the JSON payload into the API, it sends all the probes, okay? You process it, and you can get the result. And there's a good old JSON definition of here's the target, message, which kind of thing I want. I want a ping, how many, etc. How many probes you want, how to select. Just the same as the web page, except it's an API. And why do I like an API? Because, of course, I can program it. But considering what the talks we heard yesterday, I have a challenge for you, which is I'll give you a really good dinner if you create an AI front end to the API that actually takes a problem description and drives the diagnosis through the Atlas probe system. Right? So there's a challenge for you. One other thing is, note that this is provided to you by the RIR system. Okay, this is the members are actually supporting this and supporting tools. You don't have to be a member of the RIPE community to use the probe. You just need to host a probe and talk to that woman there who gave me the drink. If you are in a place that doesn't have many probes, we need more in certain areas. And by area, I mean topology, not so much geography. Like if you're in a network that has no probes, etc. So you just need to host a probe. If you have one probe, you have full access to the system. One other thing is a lot of my probes are a little old. They're version 3 probes. They have a disease. They get sick USB keys. It makes you crazy. Here's my solution. I replaced the little USB key with a compact flash. Believe it or not, this stays much more stable. I don't know who out here has version 3 probes with USB problems. Right. So, and that's it. Questions? Thank you very much.
Thank you, Randy, for that informative talk. How many people, just a show of hands, use the RIPE system, the Atlas probes, or the... So there's a great opportunity to increase the visual topology look by getting a probe, or even setting up the virtual Atlas and talking to Leah to help you with that. I use it quite a lot in my work to encourage people to keep traffic local and demonstrate how you get that shoehorn effect or the trombone effect going out of country and back again when you're trying to talk to other organisations. So I'm hoping that our next presenter is in the room. I haven't had a chance to confirm. So Katerina is going to be talking about To Space and Back, integrating next generation terrestrial and satellite communication networks. If you're in the room, can you come up to the front now? Oh, you're over there. We need to talk a little bit longer while she's doing that. So, I'm good at dancing. There's lots of social media there. So talking about the lineup, we've got actually 3 more presenters. So it's good that Randy was a bit ahead of time because we've got a lot of content to cover in the 90 minutes. So our third speaker will be Keo Sun, who's going to be talking about network timing. And then we've got the last speaker, Zahir, who's going to be talking about campus network bandwidth. Let's put our hand together for Katerina.
Thank you very much. How are you? No. Yes. Okay. Thank you. Hello, everyone. I'm Katarina Stefanovic, a wireless access network optimization engineer from Telekom Serbia, which is major operator in Serbia, and also I'm a RIPE Atlas ambassador because I enjoy learning new things about internet and how it functions. So take your seat, because today we will have the journey from here, from Earth to space and back. So, what we will learn on this journey? What is the motivation of expanding satellite communication? Thus, we have a huge gap here with terrestrial networks, and how we cover this huge gap. Why routing behaves differently in satellite communication, why I chose RIPE Atlas as a useful tool to measure these things, and what is my use cases and how I show why we need to think about non-terrestrial and terrestrial network interoperability in the future. So I would like to start with one good quote from Carl Sagan. Does anyone here in the room read or maybe listen to Carl Sagan, or please your hand up? Oh, you're a space-aware person here. So I want to start with this quote because he said, "We are just a tiny dot in a vast cosmic arena, and how we can manage to connect an entire planet. Does it come with satellite connection or just terrestrial connection, or is a terrestrial connection enough?" So, first of all, I want to start with that global connectivity is not global. Why I think in this way? Because internet connectivity depends on routing decision, not only on physical distance. A large part of the world are still lack on reliable terrestrial communication. And end-to-end latency is often driven by routing policies, not just geography. So even today, global connectivity is still shaped by where infrastructure exists and where it doesn't. So by the GSMA report, which was 2 years ago, 3.4 billion people still remain unconnected to modern internet services. So yes, this is a huge number, but this is not because we only lack of satellites, but limitation of terrestrial networks due to geography. Roughly, in Asia-Pacific region, we have around 80,000 islands. Also, we have so many mountains, ocean, which needs to be connected to the internet. Also, is it possible to deploy fiber and base station in any remote area? Is it difficult? Is it expensive? Also, we have limited peering and backbone access, and political and regulatory constraints. For example, China not allowed to use Starlink connection, just their own LEO constellation, which is in deployment now. So this number doesn't mean we lack satellite. It means that terrestrial infrastructure is not enough. And on this slide, I just want to show that roughly 80% of Earth's surface lacks reliable terrestrial coverage, which you can see also. So how do we manage to fill this gap? With adding another routing layer to the internet, let's say, with a LEO satellite, or let's say low Earth orbit satellite. This is not replaceable. This is complementary technology to terrestrial network. And these facts requires measurement-based evaluation, not assumption. And that's the reason why I choose RIPE Atlas, to measure these things, not just simulate it. And first of all, if we want to talk about measurements, we need to talk about routing and we need to talk about architecture. So how looks like architecture in LEO satellite system? For example, if we want to just surf on internet or watch some movie on the Netflix, we send this request through packet from our PC, then to the Starlink phased array antenna, which is used terminal, and you could see it on this slide. Then our packets go from Q and K band to the satellite. And if our satellite, let's say it's a lucky guy, and see the ground station near Netflix server, then the packet go to the ground station, then to the gateway, then to the point of presence, and enter the internet backbone and reach their target, which is, for example, Netflix server. But if our satellite is not, let's say, happy, and if it doesn't see the ground station, then we use laser inter-satellite links, which means that we connect satellites through lasers. And we will talk about it later. On this slide, I just want to show you that we have so many Starlink point of presence in Europe and USA, but maybe in Asia-Pacific region, you can conclude that we needed more. And this will improve and latency and reliability of this kind of network. On this slide, this is just one simulation, which I link right down on this slide. And I wanted to show you what user terminal could see. This is my country, Serbia. And I located the user terminal in this bold green cell. And this ellipse could show you what this user terminal could see and how many satellites we could see just from one point of view. In this situation, we could see 13 satellites, and the bold green line shows the nearest one and the best one from our user terminal. And I also did it for Jakarta, and as you can see, we could see only 4 satellites. So that's the question for you as a public. Why we see fewer satellites in Jakarta? Is this because of longitude and latitude of user terminal position? Is it because of the weather? Or maybe just elevation angle of the satellite? And this picture shows us inter-satellite laser links, which could be interplane, between different planes, and intraplane, in the same plane. And inter-satellite links allow packets to stay in orbit, enabling non-geographic routing paths. And that's the reason why I think LEO Starlink is not a radio link, it's a new autonomous system number in the internet. And that's the reason why I want to say that we just add new routing layer on the internet. And when we know what is the architecture behind the satellite communication, I just want to talk about why I choose RIPE Atlas to measure the performance of the Starlink network. First of all, my RIPE Atlas probe looks like this one in the slide. This is the, I think, older one probe. This is the hardware probe. You can just install some software probe on your router or virtual machine. And on this map, you could see the concept, how RIPE Atlas platform function. And the RIPE Atlas controller is the brain of the, let's say, all the platform. And I think Randy have a good description what RIPE Atlas is. And on this map, I just want to show you RIPE Atlas coverage, that we have so many connected RIPE Atlas probes in Europe and in the USA, but maybe in this region we needed more probes. And this is how RIPE Atlas platform look like. This is really straightforward and user-friendly because you just go to ripeatlas.net, then to the slide menu, click to the measurement, create, then you can choose between several measurements. In my measurements, I pick ping and trace route. Then you can set some configuration about your measurements, which protocol you use, how many packets you want to send, what is the size of the packet, and so on and so on. And you can also set the timing. And this is how measurement results look like. And then, because architecture defines possible paths with measurements, I reveal actual paths of the network. So I'll go quickly through this slide because lack of the time, but there is a huge impact on latency, and this slide just want to represent what is the impact on round-trip time when I measured the round-trip time on RIPE Atlas. And this is a huge impact from architecture, congestion, handover, then radio interference, fading. Also, we have propagation effects, like especially in Starlink communication and solar and magnetic radiation effects. But you can go detailed on the website. And my setup for my measurements is, the goal for my measurements is end-to-end comparison between terrestrial, mobile, and let's say LEO satellite network. Perspective is to show end-to-end performance. I use measurement platform, which is RIPE Atlas platform, which I represent you. Then I use RIPE Atlas probe, which is connected with a different access network. And I chose RIPE Atlas probe from overlapping countries, just to eliminate location-dependent latency effect. So I conducted same measurements, which means ping and trace route, and in the same timing. For 7 days, I sent 3 packets. So the goal of this measurement was not to optimize network, but to observe how internet routing behaves when only the access technology changes. And this is the 2 different access technology in my measurement setup. First one, I would like to say it's terrestrial mobile, but I mean fixed wireless access network, where I have a 4G and 5G router connected to the base station, or let's say nearest base station. Then I have stationary user, stable radio conditions, so I can focus on core network and inter-domain routing. And the other access scenario is, let's say, Starlink router, which is connected to the router and to a RIPE Atlas probe, and we have really dynamic space segment and alternative non-terrestrial routing paths, which I will show you in my measurements. I have 2 cases. One case is from Japan to Europe, because I found, let's say, one fixed wireless access, one probe which is connected to fixed wireless access, and one probe which is connected to Starlink router in the same country, which is Japan. And I measure what is the round-trip time from Japan and from that probe to my target probe in Amsterdam, which is in RIPE NCC. And also my second measurement case is from Europe, and I chose probes from overlapping countries to Asia, and my target probe was Singapore. I just wanted to measure intercontinental routing with tier 1 transit dominance and long-haul paths, or let's say round-trip time on long-haul paths. So let's go in detail about these cases. Why Europe to Asia? Because this is the one of the longest intercontinental internet paths. That is strong dependence on tier 1 transit and routing policies. There is idle for exposing path inflation and routing detours. And why I chose Singapore, you probably ask yourself, because this is one of the major Asia-Pacific internet hubs. This is dense tier 1 and content delivery presence. And this is a really stable and globally reachable destination. And on this slide, I want to show you mobile and, or let's say, fixed wireless access source probe from overlapping countries. And overlapping countries, in my case, Austria, Bulgaria, France, Germany, Greece, Italy, Netherlands, Sweden, and United Kingdom. And on the second slide, I want to show you Starlink source probes, which I included in my measurements, also from the same country: Austria, Bulgaria, France, Germany, Greece, Italy, Netherlands, Sweden, and United Kingdom. And you can conclude that we have fewer Starlink probes because it is a relatively new network. And in my round-trip time average distribution from Europe to Singapore, we can conclude that observed round-trip time values span approximately from 180 milliseconds to 400 milliseconds across transcontinental routes. And in this picture, we could see that average round-trip time is in mobile, or let's say fixed wireless access network, much higher than in Starlink. Then we have also higher jitter and extreme outliers. But in Starlink, we have lower round-trip time and narrower distribution. Then I represent hop count, and on this slide, you could see that Starlink have maybe more hops, but lower round-trip time. And that's the reason why I think that hop count is a poor predictor of latency when routing policies dominate. And the next slide, I want to show you a really good, let's say, tool on RIPE platform, which is Kipu, and which is really, really good to show me traceroute results when I use so many sources, which I represent to you. And on this slide, we can just see that from traceroute, a really good representation of satellite architecture, that we have Starlink, LEO access segment. I just don't go through details because of lack of time, but we can see Starlink LEO access segment, then exit to Starlink point of presence in Frankfurt, then peering with NTT, then long-haul fiber Europe, Singapore, and then reaching their target, which is Singapore. Also on this slide, we could see traceroute analysis, but in this case from fixed wireless access probe in German to the Singapore target source. And we also could see that we have, first of all, LTE, or let's say long-term evolution access, then routing through Vodafone, and then enter the Tier 1, let's say, backbone, and then go reaching their target in Singapore. On this in these two slides, which I will show you, we could see one reasonable and let's say one irreasonable routing policy. In this first slide, I show you one outlier from my plot, which is Sweden, mobile probe in Sweden, and target also in Singapore. And we can see Tier 1 detour case when packets go through 7 different cities and change 3 Tier 1 providers. And this is caused by BGP policy, not geography, of course. And the next one is really reasonable routing policy from Italy to Singapore, also mobile probe. Their mobile probe, or let's say packets, uses geographically sensible route. We have no intercontinental detours, and round-trip time is comparable to Starlink. And my last case is Japan, and I chose it because I have overlapped, I have the Starlink and the mobile probe in the country, and I measure round-trip time to Europe, and let's say to Amsterdam, to RIPE NCC, and I chose Japan because also it's one of the major Asia-Pacific internet hub. And what is the key observation of these measurements is that we could see in Starlink network that egress point is changed day to day. It is possible because we have some failures or we have some congestion on the backbone, but what we could see in mobile, let's say fixed wireless access probe, is that we have single fixed egress point across all trace routes. And on this slide, I will not go to detail because of lack of time, but you could see how they change egress point in detail. Okay, this is the double slide. And key insights, my measurements, is that hop count is not a reliable latency indicator. Tier 1 presence does not guarantee optimal paths. Mobile network suffers more from core congestion and policy-driven detours. Starlink benefits from early backbone entry and more flexible routing, and routing architecture dominates access technology. And then, when we know these facts from my measurements, we need to talk about non-terrestrial and terrestrial network interoperability. This is practical necessity or our future vision. And in this slide, I just want to show you that Starlink enables connectivity where terrestrial network fails, just in remote and rural communities, in islands, in maritime environments, in emergency and disaster response, and also in some remote research or educational part of the world. And my future research will measure end-to-end latency, but this time on application layer. Then I want to use all Starlink-enabled probes on RIPE Atlas platform for multi-continental comparisons. Also, I want to compare 4G and 5G core latency and dual-stack routing behavior and detect anomalies and evaluate inter-satellite link impacts on long-haul efficiency. And for the end, space may be dark, but the future of satellite communication is bright, where connectivity will meet interoperability day and night. So thank you for your attention. And is it any questions?
Thank you very much, Katarina. I'm Husni from Soy Asia. Actually did a bit of a Starlink measurement probably a couple of years ago. We had 2 sites in Indonesia. I think in terms of the RTT and latency, this is something that I still cannot get my head wrapped around this. Because if you see this, let's just say if you're doing ping with 1 second interval, it's a very much different compared to you doing UDP with 30 millisecond interval. So I can show you my data if you like to see it, but probably this is something that I like to suggest for you to do in the next round, since you're going to do the application layer. So that's my suggestion, and probably it would be good if we can talk on the details on that. Thank you very much.
Thank you for your advice.
Are there any other questions?
Thank you.
So thank you, Katarina, for your talk there. Very informative, and it showed a real-time application of the talk that Randy was talking about in regards to using the RIPE Atlas for measurements. So I'd like to now call up our next speaker, Kohei. I'm sorry, I do apologize.
That's okay.
He's from Seco Solutions, that's going to talk about network timing and GNSS independent fact. So thank you. Put your hands together.
Is this quicker? Oh. Okay. Oops. Okay, good morning, everyone. I was a little hungover. So today I'd like to talk about timing. Usually we don't see, but every day you guys are using precise time. This is okay. Younger, they Mazu-san and Achi and me in Kyoto, maybe. I was doing a network society for more than 15 years. And I'm also attending the timing society like ITSF and WSTS, ISPCS, and also interoperability community in Europe, and also Apricot here. Okay, This, I think, IEEE ISPCS is a major event, interoperability event, and ITSF is a timing community, very niche community in Europe, and WSTS is also timing community in US, and ENTC is an interoperability organization. And I hope this session will help users, vendors, manufacturers, research institutes, and government bodies understanding of the latest situation of timing situation. Okay, first I'd like to let's start with GNSS. GNSS stands for Global Navigation Satellite System. GNSS stands for Global Navigation System. It provides positioning, navigation, and timing information from satellites. Major systems include GPS from US, QZSS from Japan, and GLONASS from Russia, Galileo from EU, and Beidou from China, which are widely used worldwide today. GNSS is a fundamental time source for many infrastructure. Okay, GNSS provides three key functions: positioning, navigation, and timing. Among these, timing is extremely important because the infrastructure systems require common and accurate time reference, often with UTC traceability. Why is timing so critical? First, positioning itself depends on accurate time measurement. Even nanosecond level errors can cause meta level positioning errors. Second, many infrastructure systems rely on time correlation such as log analysis, transportation systems, and distributed services. Okay, there are two major protocols used in time synchronization. As you know, so many people here know about NTP. NTP is widely used and provides millisecond level accuracy, which is sufficient for general IT systems, of course, internet. On the other hand, PTP provides microsecond and even nanosecond level accuracy, which is required for telecom, mobile, finance, and power utility. These days, CRONI is widely used, became major and widely used by mainly Linux distributions. Let me explain some details of PTP at this session. Okay. PTP allows a high precision time synchronization over IP or Ethernet network. Typically, Grandmaster clock receives the time from GNSS, and time is distributed across the network via these devices rather than switches. This architecture enables sub-microsecond synchronization accuracy. Okay, and PTP has so many profiles. PTP has been standardized in multiple profiles for different use cases, and these profiles have evolved in different directions. IEEE and ITUT and SMPTE. Okay. First, standardized by IEEE in 2008. And then second, ITU-T standardized G.8265.1 for simply in order to synchronize routers and switches and end node. And then ITU-T standardized G.8275.1 and .2 for mainly mobile. And these days, power utility companies adopting PTP technologies and IP network for their distribution system. And also industrial like FA, factory automation and sensor network are using this GPTP standardized by IEEE. And also broadcasting industries are using SMPTE. So, and these days, IETF standardized RFC 2760 enterprise profile for PTP last year, mainly for AI and data center, and also OCP, TAP. This is a kind of a open computing project, is developing the data center profile. Okay. In PTP network, there are two important concepts, boundary clock and transparent clock. A boundary clock, BC, regenerate and time and distribute it downstreams, helping scalability. A transparent clock, TC, measures residence time inside the switches and correct delay without regenerating the clock. These mechanisms are high accuracy synchronization across large network like mobile. Okay, let me explain how boundary clock works. Boundary clock receives a PTP packet from an upstream master. Based on those packets, it synchronizes and regenerates its own internal clock. Then the generate time is redistributed to the next hop, and finally to the slave devices. This means boundary clock acts both as slave and master. As shown in this diagram, this architecture helps improve scalability and allows a larger number of devices to be synchronized accurately. So this boundary clock is widely used for mobile network these days, especially for 5G. Okay. Next, let's look at the transparent clock, TC. Unlike a boundary clock, transparent clock doesn't regenerate the clock. Instead, it measures how long a PTP packet stays inside the switch, which we call the residence time. This residence time is written into the PTP packet forwarded to the slave devices. By correcting the delay in this way, the network can maintain high synchronization accuracy even across multiple switches. In short, boundary clock regenerates time, while a TC transparent clock corrects a delay. Okay. Now let's look at PTP, where PTP is used today. High precision timing is becoming essential for many types of critical infrastructure, as you see. In mobile networks, especially 5G and TDD systems, accurate phase synchronization is required. In broadcasting, PTP enables precise synchronization of video and audio stream. In finance, UTC traceability is mandatory, and precise time is essential for high frequency trading. In power and industrial automation, synchronization is used for protection systems and sensor coordination. And more recently, AI and data center environments are also beginning to adopt PTP to synchronize GPUs and storage and distributed system. Let me see. Okay. Although PTP is critical for high-pressure applications, but NTP is still widely used in infrastructure, as you see. Many systems such as transportation, broadcasting, telecom, finance, and medical systems rely on NTP for general time distribution. Public NTP servers are available on the internet, but they have several limitations. For example, public NTP doesn't have any SLA and also has security risks, such as amplification attack exist, and accuracy or reliability cannot always be guaranteed. For these reasons, many organizations deploy their own NTP appliances in enterprise environment. Okay, this is an example of NTP in transportation infrastructure in Bangkok. They're using NTP and for their own whole system. Okay. Okay. This diagram shows how time is distributed in typical railway system. Oops. Once GPS GNSS master clock receives a GPS signal to some master clock for distributing NTP packet via IP and Ethernet network to those clocks like this, and CCTV and passenger information display and in-house broadcasting. This is another example from large hospital in Turkey. More than 2,000 NTP clocks are installed across wards, operating rooms, ICUs, and examination rooms. In medical environment, accurate time and consistent time is essential for records, procedures, and coordination between departments. So they are using NTP. This demonstrates how widely time synchronization is used beyond telecommunication. Okay, now let's look at some of current challenges. First, the supply of atomic clock is becoming more difficult due to global conditions, which affects both price and lead time. Second, GNSS reception is increasingly unreliable in some regions, especially near conflict zones. Third, some governments are beginning to introduce regulations to reduce dependence on GNSS. These factors mean that GNSS continuity cannot always be guaranteed in the long term. Okay, this is a situation. This map shows where GNSS interference is being observed around the world. maybe Ukraine and Middle East mainly. As you can see, interference events are increasing in many regions. This trend highlights the importance of developing a complementary timing infrastructure that doesn't rely solely on GNSS. There are several risks associated with relying entirely on GNSS. Jamming and spoofing cannot disrupt or falsify signals. Space weather and multipath effects can degrade accuracy, and geopolitical conflicts may also affect signal availability. When GNSS is lost, local clocks begin to drift, and while atomic clock can provide a holdover, they are expensive and have long lead times. So around the world, countries are beginning to build a resilient timing network to complement GNSS. Some studies estimate that global GNSS outage could cause economic losses of more than $10 billion per day, I think more. And as a result, national timing infrastructure projects using high-performance clocks and terrestrial networks are being developed. This is a case in UK, and this is a case in Sweden. This provides by NetNode, which is also providing IX services. Okay, several alternative technologies are being explored. One is ELORan, terrestrial radio-based timing system. Another is satellite system, Aerial. She showed like a Starlink or something, but basically, Starlink cannot provide a timing because the number of the satellites are too much for catching a timing signal. So Iridium and the Iridium is providing timing by using LEO, and third approach is distributing precise time over fiber network from centralized atomic sources. Each of these approaches has advantages, but also deployment challenges. Okay. In Japan, the timing community is also actively working on these issues. For example, technical discussions and initiatives within the operator community JANOG and research institutes like NICT, contributing to the development of a resilient timing infrastructure. To summarize, GNSS-based timing is critical infrastructure, but it is not easy to be replaced. And geopolitical and technical risks are increasing. Some countries have already begun deploying alternative solutions. And network-based timing technologies can play a major role in addressing these challenges. To conclude, time synchronization is no longer just a technical topic. It is becoming a matter of infrastructure resilience and national capability. GNSS still remain important, but it should not be the only source of time. Building resilient timing networks will be one of the key challenges in the coming decade. That's it. Thank you for your attention. Yeah, because of Paul.
You talked about Crony. Oh, this is Gaurav Upadhyay from the NPIX. You talked about Crony for NTP. Is there any similar software or anything that I understand the concept of Grandmaster Clock and the BC, but can you implement the BC in the software, or it is all still very much a hardware?
Yes, basically, PTP should be processed by hardware because of the accuracy aiming nanosecond. So if routers and switches are processed by software, it makes a big, time error inside of the routers and switches. So basically, should be processed by software, hardware, like FPGA or ASIC. Is that correct answer for your?
I mean, I think I get the point because the FPGA is still a software, but it has specialized
Yep.
software, right? So it makes a difference. Can we go back 2 slides, I think? Yeah, this slide.
This one, okay.
The sync interval, I guess that is pulse per second, PPS.
Excuse me?
The sync interval, PPS, that PPS stands for
Which one?
the next, that one. PPS,
Yeah.
pulse per second or packet per second?
Pulse per second.
Thank you.
Not packet.
Hello, Jonathan Brewer from
Hi.
New Zealand. I'm just wondering, what are normal holdover times for NTP servers now? Is it like 1 hour, 2 hours, 2 days, 2 weeks?
Yeah, depending on the requirement and depending on the oscillators inside of the NTP appliances. For example, OCXO will have a day for microsecond rollover, but if you buy a very expensive atomic clock, that can sustain for more 3 months, depending on the of course how expensive and accurate atomic clock. That's a point. Okay.
Any more questions?
Thank you.
It's good to see our speakers are keeping us on time. I thought we were going to have a bit of a time crunch here, but we're actually on schedule. So I'd like to invite our last speaker up to talk about the campus network bandwidth and performance measurement case study that he's got. His name is Zahir, so put your hands together.
Life is full of puzzle. Why not? Last year I was in a fellow. See, this year I am in a speaker. So this is a change of. Same thing as a network. Network also have your puzzle. So before that, I'll ask the 2 questions. So first one, have you ever measured your campus network or your internal network? The second question, do you ever measured your campus network or your LAN network throughputs? Most of the you have answers. Sometimes you don't have. No worry about that. Once you finish my presentation, you will get the great point. Ladies and gentlemen, good morning to all of you. My name is Mohammad Mansoor Zahir Hussain. Assalamu alaikum. Aibowan. I'm a network engineer at the Open University of Sri Lanka. So I have a 14 years experience. I am very good with networking, system designing, and security, as well as open source systems. So I recently completed my master's in cybersecurity, and also I am a volunteer of the LKNOG, Lanka Network Operator Group, last 7 years. And this year I got the opportunity to work as a program committee of Apricot, as well as I'm working as a program committee member of the CENOG as well. Okay, so this is me. So let me start. The problem is, 2 years back in my campus, every day my stakeholders, including students and staff, they complain. My network is slow, even though I have a network connectivity, even though my network cable is connected. My network show it's a green color. It's not an amber color. But still, while accessing my local system, I can't because it's unreachable. So always it takes long time to file sharing. So what we do initially, so as an engineer, we start the troubleshooting. So first hand, we check that are there any issue with the authentication? Are they using the proper username and password? Second, use the ICMP protocol to do the ping and check the connectivity. Third one, use the NS lookup to see the DNS installed or not. The fourth one, we check the path using the traceroute. The last one, if there is a malware function or if there are any suspicious activity, we use the log file and identify if it is issue. But we missing one thing. That was, we never check our throughput. Are we? So that's the case to start this case studies. So it took almost 6 months to identify how I can make this possible. Okay, so through these case studies, my main scope was we identify internal fiber link, internal UTB link, that means Cat6 wired LAN, and Wi-Fi connections. So we are not to worry about internet or external link. Main goals, first we identify if there are any bottlenecks. Second thing, check the difference between access layer, distribution layer, and core layer. And finally, we have a proper solution, so automated solution. Because in my case, there are a lot of non-technical users. My stakeholders are non-technicals. Okay, let's move. So first we have to identify what are the layers. So there are 3 layers: core layer, distribution layer, access layer. The core layers are working as a layer 3 devices, such as routers, core switches, firewall. In distribution layer, mostly layer 2 devices, it is switches. At the third layer, access layer, this layers users using the end devices, stakeholders. Okay, so in this case, I use mainly 3 tools. So very first one IFERP, second one is Libra, third one is SmokePing. So let me go to the IFERP. So if you are looking for a depth analysis, if you want to really see what is inside the packet, each packet how is work, best option IFERP 3. This is more technical, right? It is server client based architecture. Same time, it can be support Windows as well as Linux. If you are using the Windows, much better use with the PowerShell command, right? During the presentation, during the demonstration, you can get the clear idea. Okay, so this is sample methods. So if you want to run IFERP, so you can use the server side, somewhere in server environment and somewhere in a client environment. So all these files are in my GitHub. You can make the testing. So during the demonstration, you get a great idea. So let's move to the second option. It is automated method. It is very simple. if you're very good with the Linux, you may install this application. All the repositories files and supportive files are available in GitHub. So basically it's work on Ubuntu and with the Apache. And I added the LibreSpeed repositories. So it kindly use the client server model. It's a lightweight, very simple, and any non-technical guys can operate this. So within the network, if you allow the 80 or 8080 ports, that means HTTP or HTTPS, it works within the network. Just need to type the URL or IP address and press the button. It will show what is the bandwidth you are using. So for example, if it is, what's the level of ping, what's the level of jitters, and how much they downloading, how much they uploading. So it's giving a within the seconds. So you are not to worry about technical. So in my case, I have a 4,500 staff with around 20,000 students. So with the 6 people in my team, is it possible to troubleshoot each and everyone? No, this is the best method. If you have a problem, just what we said, you will go to our URL. Our URL is sp.oesl.lk. Just press the button. Then if you have a problem, please let us. Okay, the third one is smoke ping. This is really good for while you are checking your layer 2 devices. That means distribution layers. So you should know. So before you are delivering something, you have to verify your switches are working properly. So these things are working as a master-slave design. So much better to use in distribution layers. Okay, let me see the video.
Let's move on to the demonstration. Our first demonstration will be done by iFerb3 tool. In this setup, I am using the remote server as well as local client PC. On the client PC, I will open the PowerShell and do the same in the server PC as well. On the server side, I will use the command iferb3.exe_-s to run. This will start the server in listening mode. Now I will move to the client PC and run the script called network_test.ps1 in my client PC. The script will ask you to save the location. Simply I gave it to the name called ITD for my identification, or else you can type your name, preferred name, to save the log report. On the script status start running and server beginning to receive the traffic from the client, you will see the data transfer statistics on the screen. In my test, the maximum throughput shown as 94.3 megabit per second. This means the client network interface support less than 100 megabits per second. At the same time, the respective log file served in your local machine in your local PC, you can open the log later, filter by date and time to review the network performance statistics. Let's open the notepad file and see what is inside there. Through my script, I generate that file. In that file, we have ICMP command to run the ping result. Then it will show the TCP traffic transfer as well as UDP traffic transfer, and last one trace out. But anyhow, it support maximum 94.3 megabits second maximum traffic transfer rate. Okay, now move to the second demonstration. In this I am using the speed tester, which we will run on the same client PC. You will notice that bandwidth shown here is very similar to the what we serve in IFOP3 test. This is confirmed accuracy and consistent of our measurement. Next, I will repeat the same testing using another remote client PC. Here you can clearly observe the difference between this test and earlier test from my remote PC. This will be help to compare the performance of multiple endpoints. So here it will show the nearly 10 gigabit per second. Okay.
Because of that service under my server environment. That support 10 gig.
Now we'll do the third demonstration is on the smoke pin. Let's browse the smoke pin dashboard. Navigate to the distribution switches and select as a ITDS. That means my respective location distribution switches. In this ITDS switches, it will show the first 3 hours smoke pin statistics and last 30 hours smoke pin statistics and last 10 days smoke pin historical performance, how will work on this my network. This gives you clear overview of latency, packet loss and network stability of the overtime. Okay, so based on this, we will move to the conclusion. Through this demonstration, my main purpose of identify what are the possible reason of the bandwidth.
Okay, so that's how we did the demonstration. So that was pre-recorded session. So after this is the analysis. So if the throughput greater than 90%, it means it might be a problem with your cable, or if it be a UTP cable, if it be a fiber cable, or it should be a switch port. And less than 1 milliseconds, it be a jitter. So mostly you have to check with the conjunction of, or you check the duplex mismatch, might be your SFP transceivers or your network card. The third one, if it is there are packet less than 0.1, so might be a problem with the network card or switch port. It's the last one, latency. If it is the less than 1 millisecond, might be a overload segments. So this is how we get the analysis after finishing our case studies. Okay, so let me have more about things. We'll talk about the case studies number 1. The problem is slow file transfer between the 2 different locations or 2 buildings. So we use IFOP3 tool for this case. Finding is we got the 94 Mbps instead of 1 gig bandwidth. Okay, root cause, duplex mismatch on the fiber SFP port. So what is the solution for this one? We forced to full duplex mode. So in the outcome of this case, we achieved the 94 Mbps, reduced the time from 10 millisecond to less than 1 millisecond. Let's move to the next case studies. This is a sample screenshot of this. How did we this? Okay, second scenario, lecture hall users are complaining about the cannot access the systems or LMS, that means learning management system. This is from my students. So we use LibRespeed plus smoke ping. The both tools work fine for this case. So the finding, latency spike 30 millisecond, throughput is 75 Mbps. So root cause, access points are overlapping the 2.4 GHz channels. So actions, reconfigure the 5 GHz optimizing channel. Outcome, latency less than 3 milliseconds, throughput 240 Mbps. Okay, so this is how, so first image you can identify it's under the 2.4 GHz Wi-Fi conjunctions. So second one, we updated to 5 GHz. So you can see the next photos, see it will show how the bandwidth work. Okay, the third case studies scenario is a admin block. That means respective block users are complaining they have a randomly disconnecting the users. So solution, we use the libra speed to check that repeatedly are they had a problem. So instantly is the throughput less than 99 Mbps. So what is the root cause? It's a damaged Cat5 cable between the access switches, or it's a wall port, or it is not be a not higher than Cat5e. Okay. So what is the solution? Replace the Cat6 or Cat5e. Then only it support 1000 Mbps. Okay. So outcome consistent of the getting 1 Mbps, 1 Gbps or 1000 Mbps state performance during the network traffic. Okay. So this is how we did. Okay. So what we learned. So what we are can share the engineers. So before you are deploy anything in production, you have to have a great idea what do you have, what you are going to implementing. So that means you have to measure. So then you have in physically you know how to check the throughputs, right? And you have a clear idea about your network. So that means 365. All the over you should have a great. Hello. Oh, what about that? Okay. And third one is very important. Sorry, fourth one very important. Most of the people are not keep the records. They are not labeling. So always you are doing the networking, you should make the labels. So which port, where to go, where is which link you are using. Otherwise, very difficult to identify. For is it the uplink or is it in a access link over? So is it trunk port or doesn't know whether to if you have a proper cabling, much better to use. The final one, you always think about in your environment, there are more users are non-technical. So you think about this way too, you have to give the solution. If you are thinking about giving the solution with the technical, it's not easy to survive in an organization. If it is something, go more than 2 steps, that means technical. So you have to think about the technical matters as well. Okay, this is kind of operation insight. If it is duplex match, might be a problem with the fiber. If it is from the Wi-Fi conjunction, it's a problem with the distribution layer, wireless. If it is a problem with the faulty cable, it's under the access layer. If it is port misconfiguration, might be a distribution layer. Okay, so these 3 are the common issues. So even though you had a problem with anywhere in a LAN network, so might be this one of these. If it is a switch port, fast Ethernet, or it is support less than 100 Mbps, might be a fast Ethernet. So you had verified is it the gigabit Ethernet, right? Otherwise you are not getting the higher bandwidth. And you have to always, you have to confirm you are using the higher than Cat5e cable. If you are using the less than Cat5e cable, again you are getting the 100 Mbps. Okay. The third one, device. That means your end users network cards must be support 1 gig. Early days it was 100 Mbps. Okay. Let's come to the conclusion. So I introduced 3 tools. If you ask me which is best, so my solution is hybrid. You know why? Each tool had a different solutions or different answers. If you are looking for a more depth analysis, better to go IFF3. In your organization, you have a less technical people, and to manage the less technical matters, better to go for a Libra. Same time, you want to know what is inside your layer 2 devices and layer 3 devices, how they work, how they performing, how they behaviors. So use smoke ping. So my solution is hybrid. So as an engineer, you should use these 3 tools. So these are the reference. Thank you guys. If you have a question, it's a time for you.
I'll pose a question for you. So you mentioned about the end user being able to enable them. So how did you do that in your education environment? And did you do a self-service portal and the awareness program that you had for this measurement?
What can I do is I implement everything in my local environment. So I'll share that my website. We have an internal website. Through the internal website, we'll share all the links and everything. So instructions. So we instructor follow that to my end users.
So the end users, how'd they find out how to use it? What they called help desk and you told them to go run this tool?
It's generally support. It is work in a browser.
Okay, so it was your support, your NOC that did the running of the measurement.
Yeah, that's things. Okay, that last, not but at least. So I have 3 people. One is my family. They always engage me to give me a support. Second one, our PC committee members. And they also giving a great support for me. The last one, my Vice Chancellor, the Open Institute of Sri Lanka, giving me a great support with these leaves and everything. So all the support to all, thank you very much. See you.
So just one more round of applause for our 4 speakers. It was a very interesting morning and we've been able to actually nearly finish on time. We might get an early mark for that. Just to let you know, the next sessions that are coming up here, we've got in this room here the Apricot Peering Forum, and next door we've got the APNIC panel discussion on the LEO satellites, LEO at scale. So thank you for your time and see you in 30 minutes after the break.